canceled, I think you will thank me.
Are you gonna?
Please. I don't think so. My little one was like, hey, it's summer. No, it's not summer because your mother me did not get off.
Well, I mean, it's up to you whether you cancel class or not, right?
That's what I thought, but apparently not. Not for 12. If I cannot come, I have to find somebody to suffer for me. Right? Last year I had to do that. And when I came back, everybody looked at me like, we don't understand what did he say. Like, he's speaking English and he's a native speaker. Alright, so hey, I'm very sorry that people asked me what's the homework. I thought we talked about it and said we will do it in the class, but I'm very sorry to make you panic, and I don't know how to get back there. It's stupid. Download. I don't know. Okay. So I figured that we should go through this in the class in order to get you a little bit clear. Alright, come on, stay there. You know that the road is close to go to Charleston, right? So do not go that way. And do not go to Charlotte either. It's not because of hurricane, it's because there are a lot of stubborn people living there. You cannot talk to them. Okay, anyways, forget about what I just said. Alright. So here's the thing is we always, when you read this questions, they always give you as water as the material to calculate the heat capacity. So this kind of heat capacity is a specific heat capacity for water at certain temperature, at certain pressure. So when you see the standard specific heat capacity that is normally for water is 25 Celsius degree at 1 atm pressure. So with that, you will know that heat capacity might change a little bit for water if the temperature is a little bit lower or a little bit higher. But normally, all the paper, if they just tell you a specific heat capacity, you can treat it like it's a room temperature 25 Celsius degree and at 1 atm, okay? Alright, so with this, a lot of the scientists, they use water as a standard to calculate the heat capacity for other material. In this question, they have metal. You actually don't need to know what kind of metal is that. So the very big thing is, how do you calculate the heat? With this, we remember this. This phase curve, right? I think we talked about this at this class too. Liquid, gas. This is the melting point, right? This is the boiling point, right? So we know with this, the energy change. Heat is an energy, right? Is delta T change over temperature times mass, right? Times heat capacity, right? Say, are we good? Yeah. So with this curve is where you have to increase the temperature from certain temperature till they hit the melting point, right? And then with this curve, you will have the heat of fusion. And here you will have the heat of vaporization. With this, look at this. This scale is temperature. So you are at a constant temperature. Constant temperature. So you don't have any change of temperature. Are we good? If you see that flat line. So when this happens, your energy, heat, is just a mass with your heat of fusion, right? And right here will be mass times heat of vaporization. Are we good? So with this kind of a question, look at it. It will have a change of a temperature. And normally, it's stuck in your mind, the metal normally have a pretty high melting point. So with those kind of questions, you're probably looking at this scale. Okay? Alright, so here is the thing, is you have this cup that have how many water is in there? 53.9 grams of water, right? Alright, so you have 53.9 grams of water. So it was at 22 Celsius degree. Are we good? Okay, so this is all closed. Here has a temperature, thermometer, I'm sorry. And then you have the metal that heat up. This is 155 Celsius degree. Right? Oh yes, okay. So at 155 Celsius degree. Remember, when it's dropping here, what did this happen? After it dropped, okay? After metal added, what happened? It only tell you that temperature, 37.1 Celsius degree, right? In how many grams of water? Same thing. 53.9 grams of water. Are we good? Alright, this metal is here. This metal transfer the heat to this weight of water to increase this temperature. We good? Okay. So we say in this setup, your heat from water, again, equals to heat of the metal that give it to water. Are we good? So one will have a negative sign. Depends which one you define as a system or thermometer. Are we good? Alright, so can we calculate the heat of water that they can? We have a heat capacity for water, right? Okay, let's see. Is 4.184. Do we have a mass? Oh, here, that's the mass times delta T times heat capacity, right? We have the heat capacity, joule per gram Celsius degree, right? That's the heat capacity, we got this. Do we have a mass? Yes, we have a mass of 53.9 grams, right? And we times the change of a temperature. That is 37.1 minus 22, that's the 15.1, right? We good? So you calculate those energy. Equals to the energy that metal release to water. Are we good? So this equals to negative heat of the metal, right? Okay. What do we have from metal? We have the mass, right? That's the mass of the, that's C. We start with 1. This is what we are going to calculate. The capacity of the metal. We don't have that. Do we have a mass? Yes. 4.68 grams. Do we have a change of a temperature? Yes, from 155, we drop down to 37.1, right? So is 117.9, right? Am I doing that right? Oh well, you can calculate. So those two should be equal. and you calculate this, right? So you calculate from here. This you calculate as 33,405 joule equals to, this is the metal, right? The mass, the delta T, and then you calculate heat capacity of this metal. Are we good? So far? Are we good? Yes.
When I multiply 4.68 times 117.9, I got 551.7.
4.68 times this?
Yeah, I got 551.77.
Then that's 551. Wait, just you calculate and divide. Yeah.
Instead of 688. So I really
You can change that, right? This is the slide we made. They might have the malfunctional calculator. Sorry. Are we good? Are we good? All right. Then the next one. That's where you can calculate your heat capacity for your experiments. How much heat is released by the combustion of 250 grams of octane? What's the trick in here? Please read. When this should be the heat of evaporation. Here normally they may give you per gram or per mole. You do have to do the unit conversion. Are we good? Just remember, the one before we used kilojoules per Celsius degree per gram. But here is per mole. Okay? Please, if you wanna cancel out this unit, please convert your gram into mole. Are we okay? And this is where the flat line is, where you calculate your heats. Ooh, I don't want to mess up. Oh God. This you cannot see. Your heat equals your either evaporation or fusion, either fusion or evaporation times mass, or times mole, depends on the unit from here. We good? That's just the setup again. Again, the heat that released from metal equals the heat released to water. Or if anything, okay, here's a very famous question that happened at ACS. They said they put the metal in the boiling water for 10 minutes and drop that metal into this water that increased the temperature from 25 Celsius degree to 40 Celsius degree. What's the temperature of the metal before you drop in? Boiling water, 100 Celsius degree, right? So they use those kind of language they think you should know, because the boiling water at the time is at the boiling point, so the temperature should be 100 Celsius degree. Yes.
If they don't specify a different temperature or a pressure, like an
It should
atmosphere,
be 1
okay,
atm.
just assume it's 1 atm.
Yes, you should assume. But if they tell you STP, then you have to find a definition and find the pressure and the temperature. Okay? But if they say boiling water, please know that's 100 Celsius degree. And if they say that metal was in the ice water, you will know that's 0 Celsius degree. Okay, that's the knowledge you have to have from 12-11. Are we good? That's really happened on the ACS test. A lot of people suddenly freak out, aka me. I did. I was like, alright, this is another example for you to like calculate again. It has a 1 by 1, step by step. I thought this one is cool because they even give you the step and then you can just follow this and calculate it. Right? Are we good? Again, you have to have one thing stick in your mind. In this setup, the heat that released equals to the heat that absorbed. Okay? You did not lose any energy to your surroundings. So the heat that water increase or decrease will equals to, I would say, heat or energy from that particular material. Either normally it's metal. They normally use a metal. They do not tell you copper, I don't know something. They tell you it's a metal. And they change the temperature. You have to calculate the specific heat. Okay? Are we good so far? Okay. You all know that water's specific heat is 1 calorie per gram per Celsius, right? It's 1, but that's based on calorie. And 1 calorie equals 4.18 joule. That's why you normally see 4.18 joule per gram per Celsius. That's a conversion between joule and calorie. But what calorie you saw on your food container that has a C is a little bit different. That C means kilocalorie for this one. Okay. So if you saw something, I don't know if that will be on ACS. If they tell you 1 piece of a cracker, four per serving equals 4 capital calorie. That means 4 K calorie. Okay? Are you good? You know how to read those contents, right? I don't know if they will do it on the regular test, but that happened to me once because they want me to lose weight, and I miscalculated. All right, this is another example. Please do that at home, because guess what? It's on the test. Yes. Thank you. And I thought this is really, really clear. Yes.
Can you just go back to like the last time?
Yes. This one?
Thank you.
Okay, good. Oh, it's actually on D2L already right now. Hopefully, that will help you a little bit. Okay? Those please, after this, tonight you will have a homework on Newton. Okay? Are we good? For all those, 1 by 1 example, and if you cannot get it, please let me know. Come to see me. Or since I'm evacuated, I'm pretty bored. I have a 6 hours extra every single day. Okay? Can you do this? 23.6 ice cube. Ice, water cube. At minus 31 Celsius degree, it dropping to 98.2 grams of water at the 84.7 Celsius degree. Find the equilibrium temperature. Yes? Excuse me? No. It because it's ice, so it can go down, right? It's not ice and water. If it's ice and water coexisting at 0 Celsius degree, right? They are melting. But this is pure ice. It can go down a little bit more, right? So that's minus 31. So that's a very good question because I might get confused. Ice can go down even lower than 0 Celsius degree. But ice water should be 0 Celsius degree. Should be. In reality, it might change a little bit, but if you see ice water, that's 0 Celsius degree, because they are in that transition from solid to liquid. Right? That's good? So with this, what will you do? Again, you can treat the ice cube as that metal or that solid. Right? And then when this is equilibrium temperature, that means they end up at the same temperature at the end. Alright? Good so far? I see some question mark.
I have a question.
Yes.
So since they're both water, technically is the C the same, so you don't have to plug it in?
Huh?
Since they're both water, their C, wouldn't it be the same, you don't have to plug it in?
Sometimes you will.
But that would be given, right?
Yeah, well, yeah.
Oh, got it.
Yeah, you will be given that because the specific heat that you have, heat capacity that you're given at 1 calorie per gram per Celsius degree is for water. That means H2O molecule at liquid state. Yeah, but as solid state it will be different. Yeah, so every single molecule will have a different specific heat at different phase. Solid will have one, liquid will have one, gas will have one.
So where's the pointer to?
Oh, sorry. This is the specific heat capacity for ice. Then see, they go from minus 31 to 0. Okay? And remember that fly line? That's where they melted. That you have to calculate with the heat of the fusion. Good? Then after that, they will be liquid. Okay, let's do this. This is more advanced ones, okay? Time, temperature. Alright, so you have, because if you would think, okay, so the water, you will assume, or you can first assume, it's not going to drop down to 0 Celsius degree. Okay? So the hot water at 84.7 probably going down around here. Are we okay? Maybe going down somewhere. So with the hot water is 98.2 Celsius degree times the heat capacity 4.18. That's the delta T, right? So what's the minus the final temperature to, it was 84.7. That's the energy that this water will release to the ice to melt it. Then when you see this, ice coming to this temperature, we say this is final temperature. Which state that they go to? From solid to liquid, and then they melt it. And then from liquid, 0 Celsius degree to this final temperature. We say this heat is delta T times mass times capacity, right? And the heat is the mass times heat of fusion, which is 3.3 joules per gram. This is 2.077 joule per gram per 0 Celsius degree. So with this,
That 98.2 is supposed to be grams, right? Not.
oh yeah, sorry, gram.
Is that 333 like given to it?
Yes, it will give it to you. It will give it to you. Yeah.
But it's really grams.
Yeah. So the heat of the ice that absorbs has 2 stages, right? Oh, 3 stages actually. So what's the 23.6 gram times 2.077? That's times from minus 31 to 0. That's the heat that they have to need to reach this point. Then they melt it. Have to add, have to add 23.6 times 333 joules. Yes?
Okay, so this is because you're doing it for solid, liquid, and gas.
No, only from solid to liquid only.
But you don't know.
Yeah, it has a melting point. Right? Yes.
Is 2.077 the specific heat of ice?
Yes.
So the 23.6 is from.
Huh?
23.6 is the grain.
Yes. The grain of ice.
And it was like
Yes.
0.
Minus 31 because they have raised the temperature from minus 31 to 0
Right.
to reach this point.
Right.
So the energy you will need to melt all the ice. Does that make sense so far? Yeah, yes.
So where did I'm sorry if you said it, so where did the 333 come from?
It's the heat of fusion. Yeah.
It's given.
It will give it to you. Heat of fusion. Right here. And then that will go from 0 to the TF, the final temperature. Then that will be another mass times the heat of specific heat of the water times to the change of the temperature. Good?
So you have 2 different, like the delta 8 fusion and delta 8
Vapor.
vaporization, but that's if you were going
From liquid to
yeah.
gas, then you will have the heat of the vaporization.
Okay. So we're not using that because we're trying to
Because
down to
yeah, because it's only 84.7, it's not going up, right? So we just assume they will stop right here.
right.
So if you calculate those two, then you find out the energy from here is more than the energy that water will release, then you know they are staying this line. Are we good so far? Good? All right. Step by step will be in here. So please review the phase diagram or phase curve and remember which formula you will need to use. Again, if this is going up, just remember this graph. This is different temperatures from low to high. If you are in this stage, you have to have a change of the temperature. Yes.
I just had a question.
Yes.
When Wait, where? Okay. You see that big number? The 34,767.32?
Yeah.
Where did that come from? Because I think I'm missing something. It's just the.
This is probably from there.
Oh, wait, it's simplified. Not
Yeah.
My bad.
You will have a step-by-step right here.
Yeah.
You see? Yeah, then we came down here. It's from the water,
Mhm.
the hot water.
Yeah.
You calculate that. And then you add them together. This are combination of this.
Okay.
Yeah, and that should equals to, right? Oh, here. That now is here.
Okay.
We good? So you move it around. You got those, right? Why are you laughing? Okay. Are we good? Are we good? Hey, slow! Hey, slow! Hey, slow! What's your problem?
That sounds like.
Ignore that. Ignore that. That's good, right? Alright, before we go into Hayes' law, you should know something about, we say reaction has different, I'm looking for okay. You should know, maybe more like this, that's not, okay. Let's do this by blackboard. Cool. Alright. Oh, I thought this is white, but oh well. Alright, tell me if this is endothermic or exothermic. Huh? Exothermic? Great job. Great job. But with this is the change of the enthalpy for this reaction. Alright, now we talked at the very beginning. But please keep in mind, if you times this reaction by 2, okay? So you get 2 moles of this plus 4 moles of this, create are we okay? Your change of the enthalpy will be are we okay? Are we okay? Alright, so here is what will happen on the ACA. They ask you if you have 20 grams okay, of methane. Alright? Completely react based on this reaction. How many kilojoules of energy that was absorbed or released? What will you do? So what we do is, again, remember that's what? Let's do 12 plus 4, that's 16 grams per mole, right? Are we good? So how many mole of methane is in here? One point 1.25 per mole. When they say completely react, what does that mean? Oh, use it, right? So you are looking at 1.25 of this, right? Completely react. That means your delta H has to times 2, 1.25. That's the energy you are going to get or you absorb. Are we good? Are we good? Alright. This is something, I think somebody asked me about, can we have a 1.25 in the reaction? In this case, yes, because you are calculating. This reaction has to be balanced with the full reaction, yes. But when you calculate it, you can have a fraction of it. Okay? Because you are calculating the energy. We good? Alright, so let's go into the Hayes law. So for Hayes law, again, enthalpy is a state function. If from point A to point B, you will have the same change of enthalpy. Doesn't matter what's the path. Okay? So we are looking at, I am having a fever. I want my little one to give me a medication from her school. I thought that would be 15 minutes. At the end, I will get cured anyways, or killed anyways. But I thought she will come back at 15 minutes, come back home. But she might go back to buy a candy or milk and come back. That's 30 minutes. At the end, I'm still getting medication. This state will not change. But the path that she came back from school to house to give me the medication can be different. Are we good? So the heat, every single step of a heat might be different, but your delta enthalpy will be the same. So that's enthalpy is a state function. And with this, why do we need this? Because some of the reaction we cannot see it. Like here has a very good example. Graphite, okay? Plus 2 of a carbon with 1 oxygen will create 2 of a carbon monoxide. Very simple reaction. Oh, not equal, sorry. 4. Alright? This is hard to measure because there's not a very good ways to do this measurement. So what we do is we create 2 or 3 steps of reaction. At the end, we calculate how much of enthalpy that will change and tell us whether if we do this reaction, are we going to explode the whole room out of nowhere or we will be safe. Alright, so with this we do, this is really good reaction that we can measure. Alright, and at the end we have a 2 carbon monoxide plus, well, create 2 . Alright, so we do those 2 reactions. At the end, we will create 2 carbon monoxide. But see what we need. We need 2 graphene. What? Graphite. So what we have to do? So with this, are we okay with this? Alright, so let's put another one right here. There's the 2 reactions. Let's see what we can have. So this cancel out, right? Are we good? We can cancel one of those, right? So the net reaction is 2C plus O2 to CO. That's how they make this reaction possibly to get measured. So what happened is, with this, they calculate. I'm sorry. This I will give you delta H minus 39. Oh no. 393.5 kilojoule. And this reaction is minus 56 kilojoule. But because we have to time this to 2, so what we actually have times 2, right?
No,
this, the bottom one, oh no, sorry, is the top, I'm sorry. 393 times 2. $787? What? 787? And this was 566 kilojoule. So this main reaction, the delta H, is, you add them together. So definitely minus, right? 3, 5, minus 1,353 kilojoule. Huh? Oh, sorry. Minus. Yeah, because it's minus 3, I'm sorry. Minus 393.5. Okay? That's how they do it with Hayes law. Because delta, the change of enthalpy will not change even you change the path. So at the end, so this is how the scientists know if we do this reaction, we'll still be alive. But they do not think that this will kill them. But at least with this reaction, the energy that release or absorb will not create too much of a damage. So that's another thing for you guys doing the magnesium, burning the magnesium, because if you burn, that might hurt you. But there's another way. You do different steps of the reaction. At the end, you can calculate how that will give you the different enthalpy at the end. Go back to this original reaction. Are we okay? Okay. So there's another thing to calculate the change of enthalpy. That we can do is, we actually can do, can I erase those already? So for this change of the enthalpy, we can do, okay, we say the standard. If you ever see this standard that normally at STP, okay? The standard that means nothing else. Okay, the change of enthalpy for this reaction can be calculated with the sum of the delta H of the reactants minus the sum of the delta H of product of reactants. Because every single compound has its own delta H formation, standard delta H formation. For example, I want to show you. Bear with me, we'll be done soon. Oh, by the way, you guys, the average score is better than the other session. And apparently, because I never taught, apparently the first test should be the worst, and you'll get better. Yeah. 65? All right, hey. Okay, let's do this. So that's 90.3. This is minus 2 for 1.8. this is minus 45 joule, 0 kilojoules. So in order to calculate this reaction's delta H, you can do is, now you can do the computational estimate by using Spartan. You guys used Spartan before, right?
Yeah.
You can calculate the standard entropy for every single one, right? Or enthalpy for every single one. So for this, you can do the delta H formation standard is, you have to times to how many moles, right? 4 of the delta H form of NO, right? That's good? The product plus 6 delta H H2O, right? Good. Minus 4 of the delta H. Let's do this. And H3, right? 5 of the delta H O2 in one bracket, okay? Then you should have your standard formation of this reaction. Do this at home. Give it to me on Friday. Oh, no, I don't. Okay, sorry. It will be D2L soon. I will write it down, but go ahead.
So you want to take a picture of you.
Huh?
We want to take a picture of you.
Well,